Team's project was a joint 154-106 effort to create a self-rocking chair mechanism. My name is Anthony and my responsibility was the force analysis.
My name is Tad and I was responsible for the kinematic analysis for this project.
My name is Zach and my responsibility was the geometric design.
My name is Brian and my responsibility was stress analysis.
Producing this system would enable people to enjoy the health benefits associated with the release of endorphins that occurs during the soothing path of motion. Positive effects have been observed in autistic people coping with stress, agitated babies who need to be calm, and elderly people attempting to alleviate joint pain. In order to provide this functionality, we evaluated geometric concerns and chose regulatory movement variables to define the desired rocking motion.
One of the major goals of the project was to create a mechanism that oscillates from one extreme position to another with equal timing in both directions and a constant input speed of 22 RPM. The input link was constrained to move no more than plus or minus 35 degrees from the negative y-axis. A vector loop equation of the linkage was developed and used to determine the position of the input linked with respect to the crank angle. The resulting graph shows a relationship that is clearly sinusoidal, thus confirming the extreme travel positions desired and showing the oscillatory motion is smooth. Using equations 6.18a and 6.18b from Norton's design of machines, the angular velocity of the links was determined and plotted. Again, the near sinusoidal nature of this plot just supports the determination that there is no abrupt change in speed at any time.
A 6-bar linkage system was considered to assess the total motion output and driver diode input on a single 2D plane. The force analysis was utilized to determine the maximum motor torque required to initially drive the system from a standstill position. Free body diagrams were compiled to correlate reaction forces and reduce the total number of unknowns to 17. Only 15 equations were available, so the multiple link pin joint connecting the 6-inch coupler and driver links were used to supply 2 additional equations relating the X component and Y component forces acting on the pin. Finally, the mass of the pin was deemed very small, about 0. Now the unknowns were equivalent to the number of equations and matrices were employed to find the solutions. The most relevant equation considered no applied load from the attached seat. The calculated stall torque was 11.315 pound-force inches. A SolidWorks motion analysis value of 12 pound-force inches was used for verification.
The biggest geometric design challenge was designing a way to mount the mechanism in space so that it be firmly planted to a ground plane and yet still allow for full range of motion. Early designs accomplished this, but proved too hard to construct with given equipment. Another challenge lied in reducing friction during motion. This was solved by using press fit bearings at pivot points and brass washers between each link. Pictured is a final project design that minimized friction while allowing for full range of motion. It also allows for a full-size chair to be mounted as desired. All components are machined at the ME41 machine shop using the available mill machines and lathes. The links and motor coupler were made with cold rolled steel, while the grounding post, spacers, and mounting bracket were made from aluminum. Great care was taken in machining each piece to avoid impeding the applied motion, and as a result, the final product moved smoothly and as intended.
Our initial applied load goal was 100 pounds distributed along both couplers. For stress analysis, we assumed the load is uniformly distributed along these couplers. Regions which we chose for stress analysis were the coupler and the rod which is attached to the driver diode. Before our analysis, a few assumptions were made about the material. We assumed that the material was ductile and homogeneous throughout. We also defined failure when material yields. The coupler can be modeled as a beam with fixed ends and has a uniformly distributed load along the coupler. The rod can also be modeled as a beam with fixed ends with a single force pushing on the rod. Since the rod is in motion, we can use the values found from the force analysis. With the intended 100-pound load, we had a safety factor for the coupler of 3.2. With these safety factors, we can expect the chair to withstand 100 pounds comfortably.